All right, so we'll take a look at some examples from the solutions module here in ALEKS. And the first question here is looking at predicting the products of dissolution, which is when a substance dissolves, and typically that substance is going to dissolve in water. So we need to decide what are the major chemical species that are present when this particular compound is dissolved in water. And it says that water itself is going to be present, so we can list that with each, as one of the species present. So for example, if we look at the iron 2 iodide, which has this chemical formula, and then this is dissolving in water. All right, so we know that H2O is going to be one of the species present. And then this, we need to decide, is this going to be ionic or covalent? Okay, because that will determine how this is going to dissolve. So what tells us whether it's ionic or covalent? We look at the types of atoms involved. There's a metal in here, iron. So then this is going to be ionic, which means it's going to break apart into ions. So we need to figure out what are the ions that are present in Fe, I2, iron 2 iodide. Well, we know that we have the iodine or the iodide ion, which is the I minus. Remember, iodine is in group 7, will form a -1 charge. And then we have 2 of these, right? When this itself breaks apart. So we have 2 of those. That'll give us a total charge of 2 minus for both iodides, which means that iron then, in order to cancel out those 2 negative charges, the iron has to be 2 plus, right? So remember, iron is one of those metals that can form different charges. We need to figure it out based on what the charge on the non-metal ion is. So in this case, the iodide is 1 minus. We have 2 of them based on the formula, which means the iron then needs to be 2 plus. So the other things present then, this FeI2 will break apart into Fe2 plus, and then we're also going to get I minus in that solution. And that's different than if we have a covalent compound, so something like the third one, propylene glycol. So we have C3H6OH2. Okay, is this ionic or covalent? When we look at the types of atoms involved, these are all non-metal atoms, so then this tells us it's going to be covalent, which means that when this dissolves, it will not break into ions. This will actually dissolve as individual molecules. So this entire thing will stay together. So in solution here, we're going to have H2O, right? That's the major species present. And then we're going to have the C3H6OH2. That entire thing is a molecule. And that's when you have a sample of this, made up of billions of these molecules, they just break apart into individual ones. They don't break apart into ions because this is not ionic, right? So they dissolve as whole molecules. All right, let's take a look at the next one. So it says predicting precipitation. All right, so precipitation is an example of a double replacement reaction. And this, we saw double replacement back in the earlier chapters. And specifically now, in a precipitation, we form a precipitate. Right, and a precipitate is an insoluble, so this would be then a solid product that's made. Okay, and how do we know that an insoluble or precipitate is going to be made? We have to look up in the solubility table to decide whether an ionic compound will be soluble or insoluble. So let's take a look at an example. We'll do the first one. So you're given the chemical names for these. So we have, let's do, we'll do the first one. So manganese to bromide. That's in the first solution. And then the second one, we have zinc sulfate. Okay, so remember, these are examples of double replacement reactions where all we're going to do is take the metal from one. We're going to switch it. We're going to combine it with the anion for the second, and then we'll do the same thing. We'll do the metal from the second one goes to the non-metal ion with the anion for the from the first one. So we just swap the metals. In other words, we end up then with zinc bromide, and then we're going to get manganese to sulfate. All right, so all we're doing is just predicting the products based on the double replacement, and then we're going to look these up in our solubility table to see whether any or either of these are either of these insoluble. Okay, I'm going to look up in the solubility table. So you'll need to look that up in your textbook. So here's a solubility table that you can use. Now, you do not need to memorize this. Okay, if you need this, you'll be provided with it on your quiz or your exam, but you'll need to use it for your homework. So all we need to do is to look up these compounds that we predicted from the solubility table, and then just use the table. So we have zinc bromide. So zinc bromide has the bromide ion in it. And according to this, bromides will be soluble, except if it's combined with any of these. We don't see zinc on here. So that means as an exception. So zinc bromide will be soluble. It will dissolve in water. It will not form a precipitate. And sulfates. So this manganese 2 sulfate, it says all sulfates are soluble. So they will dissolve, with the exception of any of these. We don't see manganese on there. So this will also be soluble. Okay, so then no precipitate will form in this example. Let's take a look at another one. We have iron 2 nitrate and potassium sulfide. Okay, so iron 2 nitrate and potassium sulfide. We're going to do the same thing. We're going to swap the metals. So we end up with iron 2 sulfide. And then we're also going to get potassium nitrate. And we're going to look these up now, these products on our table. So potassium nitrate has the nitrate in it. Let's see, nitrates right here. All nitrates are soluble. So this then is this will dissolve. This will not form a precipitate. And then the iron 2 sulfide has sulfide in it. Let's see, the sulfide is the S2 minus. So there it is. And sulfides are generally insoluble. So right now we're thinking this could be the precipitate. Let's see if there are any exceptions that include iron. No, iron is not in group 1A and it's not ammonium. So this then will be your precipitate, because this, according to the table, it's insoluble. All right, and then we'd need to come up with the formula for this. Okay, so iron 2 tells us right away that we're dealing with Fe with a 2+ charge. Sulfide is the sulfur with a charge on it. 2-, it's in group 6. So then we just combine these. Obviously, they're going to combine in a 1-to-1 ratio to cancel out the charges. So this will be the formula of the precipitate that we want to include here. Yes, we do get a precipitate, and FeS will be the formula for it. All right, the next question looks at a very important rule that we'll see in chemistry. You'll also see it in some of your biology classes, and that is predicting whether a substance will dissolve in a particular solvent just based on the simple rule like dissolves like. Okay, and just to recap that rule, what that means is that polar solutes will dissolve in polar solvents. And then we can also say that non-polar solutes will dissolve in non-polar solvents. So the polarity of the solute and solvent need to be the same. In other words, they need to be like. So polar solutes dissolve in polar solvents, non-polar solutes dissolve in non-polar solvents. So in all of these examples that we're looking at here, we need to decide, well, is the solute polar or non-polar? All right, so in this first example, how do we tell whether it's polar or non-polar? Well, we're looking for highly electronegative elements. So for example, this oxygen here is highly electronegative, and so are the nitrogens. And this is a fairly small molecule. So the solute there is going to be polar. Okay, because we have a polar bond between the C and the O. We have a polar bond between the C and the N's on either side. And then it's asking which is the better solvent to dissolve this polar solute. Well, according to the like dissolves like, it would prefer to dissolve in a polar solvent. So which of the two options here, which is more polar? Well, we already know that water is a very polar molecule because we have two polar. Remember, water looks like this. Here we have our H connected to the O, and the same thing happening on the other side. So this is very polar. Whereas this molecule here, yes, it does have a sulfur double bonded to the O, but you also have CH3, carbon and 3 H's, very non-polar regions on either side, and it's a much bigger molecule than water. So the H2O here is going to be the better solvent because it is more polar than the other option. All right, so let's take a look at the next one, which looks at maybe a little bit of math now. So it says the solubility in hexane of the molecular compound M is measured and found to be 62.2 grams per liter at 5 degrees Celsius, right? So this is telling you that at this temperature, you can dissolve 62.2 grams of whatever this compound M is in a liter of the solvent, which is the hexane. So this is saying calculate the volume of a saturated solution of M in hexane that would contain 38 grams of M at this temperature, right? So the temperature is the same. We usually define it for solubility because solubility is temperature dependent. So the important thing here is this, right? What is that actually telling you? This is the solubility. And in this case, how you interpret that is important. So it's saying that 62.2 grams of M can dissolve, that's a maximum, that can dissolve in 1 liter of, what's the solvent here? Of hexane. All right, so in other words, you can take this and express it as an equality to make it more user-friendly. We can say 62.2 grams of M for every 1 liter of hexane. And now, maybe the rest of it is going to make a little bit more sense. So it says calculate the volume of a saturated solution of M that would contain 38.0 grams of M at this temperature. So we want to figure out now if we want to dissolve, instead of 62.2 grams of M, we want to dissolve 38 grams of M, what volume of hexane would that solution be? So we can take what we're given, and we can now use our equality here as a conversion factor. Stick this in. We want to end up with the volume as our unit, so the liter goes on top, and the 62.2 grams of M goes on the bottom. Grams of M go away. We end up with liters of hexane as our unit, and that's what we needed to find. We just need to evaluate this using a calculator, and we have 3 sig figs, so you're going to round your answer to 3 significant figures, and we have liters here as our unit. All right, and the next one, we're looking here at interpreting or visualizing what's happening in a when something dissolves, and it's very similar to what we saw before in the first question, where we're looking to see the major species present when dissolved in water. This is more visual now. So let's take a look at this second one. So it's saying, pick a sketch that best shows what the solution would look like at the atomic level. So if you take your slider and you move it across, you'll see the background here contains these grayed out images. So the background is water, which is going to be present in every aqueous solution. Okay, now we need to decide whether the solute KCl, how is that going to dissolve? Right, so in other words, is it ionic or is it covalent? Well, we have a metal in there, so right away we can think ionic. So what are the ions present in KCl? We need to break this apart. We have the potassium ion, and we're going to have the chloride ions. We have 2 separate ions. So when this substance dissolves, it will break apart into 2 separate ions, and we're looking now, they're individual things. We want to find one of one color and one of the other color. So this may look similar. So we have maybe the purple here is potassium, and the yellow is the Cl minus, and all the other, well, here we go. So this one has the same, but now you can see the ratio of this is the ratio that we want, right? So we have 2 potassiums for 2 chlorides, because when potassium chloride dissolves, right, we get 1 K plus and we get 1 Cl minus. So there's a 1-to-1 ratio, which is the same ratio that we see over on this side. So that's something to keep in mind. So decide whether your compound is ionic or covalent. If it's ionic, it will break apart into its ions. Keep track of the ratios of the ions to each other. If it's not ionic, for example, the first one here, that'll be covalent. It'll actually dissolve as individual molecules, right? So it's not going to split up. It's going to stay together. And you want to try to select the best representation. So you have a carbon, a hydrogen, and we have 3 chlorines. So maybe this looks like what it would. So 3 chlorines are the same, carbon in the middle, and an H here, and we have the same thing, right? So we have molecules dissolving rather than individual ions or atoms. All right, so let's take a look at the couple other calculations. So the dilution. So next one. And it says a chemist makes 300 mils of aluminum sulfate working solution by adding distilled water to 230 mils. Of a 1.34 molar stock solution of ammonium sulfate in water. Now get the concentration of the working solution. All right, so let's see what information we're provided with here. The working solution . So the volume is 300 mils. And then the stock solution that you use to make that working solution, the volume of that was used was 230 mils. And we're also given the concentration of that was 1.34 molar, right? Then the molar is a unit of concentration. So our stock solution here, we have volume and concentration. Our working solution, we have volume. We need to know what the concentration is. All right, so we can use the dilution equation, which is C1 V1 equals C2 V2. Okay, and the C1 and the V1 are our initial concentration and volume. And our C2 V2 are the final concentrations and volumes. So for example, our stock solution is what we're starting with, right? So that'll be our initial. So we have a concentration of 1.34 molar. That's our C1. Our V1 initial volume is 230 mils. And what we're ending up with now, the final concentration is what I don't know. I'm trying to find that. And our V2 final volume here is 300 milliliters. So I need to solve this for C2. I'm going to isolate C2 on one side, move everything else, in this case, the 300 mils to the other side. In other words, I just need to divide both sides of this equation by 300. So milliliters go away. I end up with molarity, M as my unit. I need to evaluate this in my calculator, and I have 3 sig figs, 3 sig figs, 3 sig figs. So my final answer here, going around this, the 3 significant figures. So general strategy, when you see dilution in a problem, chances are you're going to need to use this dilution equation, which looks very similar to some of the gas laws that you used previously. So it involves a little bit of algebra and then manipulating your equation to solve for the one unknown. All right, we'll continue on with some of the calculations. The next one we're looking at here is calculating the mass percent composition. All right, so remember now, mass percent is another unit of concentration, and this is simply the mass of the solute over the mass of the solution. And if it's a percentage, you're going to multiply that ratio by 100. So we need to figure out what the mass of the solute, what the mass of the solution is. So it says the chemist mixes 82 grams of carbon tetrachloride with 98 grams of all of this stuff and 27 grams of that. And it says calculate the percent by mass of each component of the solution, right? So we have 3 components, this thing, the second thing, and this third thing. So we add together now all of them to get the mass of the solution. Okay, so we have our 82 plus the 98 plus the 27, okay, whatever that gives. Let's say that gives X grams, right? That's the mass of the solution. And that would be in our denominator here. So we have 3 components of this solution. So let's say now the mass percent, if we're looking at the mass percent of the first component, which is the carbon tetrachloride. Well, according to our formula above, that will simply be the mass of the carbon tetrachloride. I'm going to abbreviate that, divided by the mass of the solution, the entire thing, times 100. Okay, so we know what the mass of the carbon tetrachloride was. That was given 82 grams, divided by the mass of the solution, which we just found up here, whatever X is when you evaluate that. And then as a percentage, times by 100, grams go away. We end up with our percentage as our units, right? And you'll repeat that for the other 2 components. All right, next one looks at calculating the molarity using the solute math. Okay, so molarity, remember, is moles of the solute divided by liters of the solution, probably the most common concentration unit that you'll see in chemistry. All right, so it says a person prepares a solution of copper to fluoride by measuring out 0.032 grams of the copper to fluoride into a 100 ml volumetric flask and filling the flask to the mark with water. So the volume then ends up being 100 mils of solution. All right, so we have grams of the copper fluoride, that is our solute. And then we have 100 mils, that's our solution. Okay, so we need the correct units now, though. We need to convert grams to moles. Right, how do you go from grams to moles? Well, you use the molar mass. How do you get the molar mass? We use the periodic table. So we look up the individual masses of these, and we can compute that. So you have 1 copper, and two fluorides. So copper to fluoride, then we add together the copper, the 1 copper and the 2 Fs. So fluorine is about 19, copper is 63 plus 38. So that would give 101.54. That's 1 mole. Okay, all I did here was add together 2 Fs and 1 copper. Look those up from the periodic table, and I end up with this. So I can use that molar mass to convert grams to moles. We've done this before in the previous last week's module, for example. All I'm doing now is just dividing by the molar mass, which is 101.54 grams. Grams go away. Moles is my unit. And whatever I get here, okay, let's say I get X moles of copper fluoride. And then I also need my volume in liters, so 100 mils of the solution. This is a metric conversion going from milliliters to liters. For every liter, there's 1,000 mils. So that's just dividing by 1,000. This ends up being 0.100 liters of the solution. Okay, so to get my molarity then, I just take the moles, so whatever I get X moles, CuF2 divided by 0.100 liters, the solution, and then whatever, let's say I get Y. And then my unit here would be molarity, big M. I remember M just means moles per liter. All right, and the last one we'll take a look at for the solutions part of it. It says finding mass of volume from the percent concentration. Part of the treatment of diabetic ketoacidosis is intravenous D5W, a 5% weight volume solution of dextrose in water. So what does that mean? So we have a 5.0% weight volume, which is the same as mass volume, of dextrose in water. So what exactly does that mean, and how is it helpful? Well, this is a mass percent or weight percent, and it's W over V. So this is weight volume or mass volume percent. And this then suggests that we have 5.0 grams of the solute, which in this case is dextrose, just regular old blood sugar, for every, remember, percent is out of 100, so for every 100 mils of the solution. Okay, that is what the percent concentration actually means. And going from this to that relationship is very important because it actually helps you solve this problem. This is saying calculate the volume of this solution that contains 3.5 grams of dextrose, right? So now you need to figure out, well, if you want to get 3.5 grams, how much volume, what volume of solution would contain 3.5 grams of dextrose? I can take this concentration and I can use it like a conversion factor. I can use it as it is, or in this case, I need to flip it because I want to end up with milliliters, the volume, as my unit. So I'll put that on top, and the mass goes on the bottom. So the grams of dextrose go away. I end up with mils as my as the unit, right? And you end up here with milliliters as the unit left in there. So all concentration units, you can interpret them, you can use them as these conversion factors as they are, or you can flip them depending on the units, right? The units are going to be your guiding light here to tell you in what form that relationship is going to be used.